right. So, what we try to do over the last lecture of today and the first lecture of tomorrow is kind of pushing a one semester course into 2 lectures, right. Okay. So, like we would kind of show, I'd start by saying to you that if you want to do modern day computer science, it's like the days when we were students, only discrete mathematics helped. With discrete mathematics you could just do computer science. Now computer science has matured, it has picked on new application areas. Now if you don't do data science, you tend to fall behind, right. But I come from a generation where where people still looked at classical problems and stuff like that. But nowadays, as you people grow, grow into, and the subject grows, newer and newer fields come, newer and newer challenges come. So, computer science these days has picked on other 2 branches of mathematics, of which I will not talk of linear algebra in this 2 weeks. So, we will talk of probability and show to you how probability helps in computing. So, the focus of the lecture of these 2 lectures is to give you an overview of the probability that you would need during this course. So, tomorrow first lecture would be again on probability, on a particular thing of probability that would be much in use, at least for this week and some part of the next week. And then we would show to you how algorithms uses probability. Fine. So, let us start with an example, say. So, I give you a coin, right, and I say it is an unbiased good coin. So, that means the probability of head is half and the probability of tail is half, and you keep on tossing this coin, say, till you get a head. On the now see the point that in the worst case it might so happen that all of your tosses might result in a tail, okay. But in the limiting case you might say that it is highly probable that I will have a head. But let us forget about that, but think of an kind of an average case, that what is the expected number of tosses that you might need to do before you get a head? 2, right. Okay. Now, I change the problem a little bit. I say I give you a coin such that the probability of head is now not half, but it is 1/3. And I ask the same question again, on the expectation how many throws do you require? Now, I generalize, I tell to you that well, the probability of getting a head is P, on the expectation how many tosses do you want to make? Half was 2, 1/3 was 3, so P should be 1 by P, right. It should be a number greater than 1, right, you cannot make. Now, what is the proof of this one? It was very well saying that well, my intuition tells me that with a coin of probability head being half, I require 2 throws, for 1/3 it is 3 throws, for a probability of P it is 1 by P throws on the expectation, remember it, on the expectation. Now, I have to prove this, right. Without proof, this is just an assertion. So, this kind of things we will see in this next 2 lectures. Okay. Now, before I go into formally setting up things, may I know how many of you know what is a random variable? Okay. So, what is a random variable? Yeah. So, you come from a mathematics background, is it? This is the first time I have heard such a correct definition. It's like, so most people say that a random variable is a variable that takes values randomly. Well, that's not the case. It's a function from somewhere. Obviously, if it's a function, it will take a value from somewhere to somewhere. We will see. Now, we will at a point of time, maybe over the course of lectures or over tutorials that Uddala could conduct, we will prove this result, that the expectation is 1 by p. But at least in this course, I mean during these 2 lectures of mine, if I am not able to prove this, but I will at least set up things such that you can prove it in the tutorial. Okay. So, we would take an axiomatic approach to probability. Now, what is an axiom? Statement assumed without a proof. All of you must have seen an axiom at some point of your life. What is it? What is it? You must have seen it. Geometry. Geometry. You never questioned when your teacher said there is only one line between 2 points. That was an axiom on which your Euclidean geometry was built. So, similarly, the subject of logic basically sets up this thing where you take some axioms and build theories on this. So, if you question those axioms, if you say those axioms are not true, your theory does not follow, right. So, we will set up an axiomatic approach and then develop things and then kind of prove results that which you already knew, fine. So, the setup is you have an experiment which has certain outcomes, and the moment we say this, we start talking in terms of sets, right. So, probability would be over a set. Think your favorite experiments, throwing dice. If you are in computer science, say you have a graph and say you are picking edges randomly, that is an experiment, right. You are say sorting, tomorrow you will learn quick sort. So, all of you know quick sort, right. Anyone not knowing quick sort? No. Okay. So, if you are doing randomized quick sort, you pick an element to be the pivot at random, uniformly at random. So, this is an experiment, right, about picking an element uniformly at random. So, you have experiments and the outcome, all possible outcomes of that experiment forms the sample space. And then you have a probability law which kind of assigns values to these events. Say for example, in your dice case, you say that all of your throws are equally likely. So, your sample space has 6 points, each one with a probability of 1/6, and then you can build complicated events over this sample space. Okay. So, what is an event? It is a collection of possible outcomes, or even put more succinctly, it is a subset of the sample space, fine. Okay. Now, as me and Venkatesh would want everyone to be on the same page, it is like I will go a little slow at the beginning, and at any point of time if you do not understand anything, do ask questions, right. Do not hesitate in asking questions, however foolish they might be, right. Never stop yourself from asking any question that you feel is legitimate, ask it, fine. Now, what is our axiomatic approach? Right. So, probability space I would say is a triple consisting of the sample space. This F is going to be kind of subsets of the sample space and a probability. Now, we will make this P follow certain rules. So, omega I have defined to be the sample space. This is collection of subsets from sigma, and P is the probability. So, I would say that P is a probability measure which takes F to 0 1, right. So, you have three things: one, a sample space, then a collection of subsets over the sample space, and a probability function taking the from any subset f of f to 0 1. You have some requirements on f. So, the requirements are the null set belongs to f and the sample space also belongs to f. So, call them to be requirements on f. Okay. Second is, if you have a subset in f, its complement should also belong to f. And third is, if you have subsets, well, it's like it would suffice if it's countable, but for our cases we would focus only on the discrete case where it's countably finite, right. Until and unless we explicitly mention, everything is countably finite here, because it is a discrete world, it is a computer world, so you can count things. Okay, the requirement is for such sets their union also belongs to f. Union over this belongs to f. So, these are the requirements on f. Now, about the axioms. These are some requirements on P. First, so P is a, as I said earlier, is a real valued function satisfying the following. First is that it, for any event A, its probability lies between 0 and 1 for any in f. Second, that over the sample space the probability is 1. Third, and this is the most important, because all the results that you know actually comes from this. So, again I make it for any countable set of events. I mean, while writing, I would not be, always too correct. So, this countable set of events A1, A2 should be belonging to F, right. So, I am talking of subsets in F. So, they are disjoint. That means there is no intersection, right. The axiom says you can now add probabilities. Fine. So, disjoint means if you take any AI and any AJ, their intersection is a null set. Yes, union of, I did not get you. See, AIs are sets. So, union of sets are defined, well defined. Now, what did I say? Probability is a measure, is a function from the sample space to 0, 1. So, the left side is well defined. Now, if you look into the other side, probability of AI is again very well defined. What I am doing is I am just taking sums. Yes, equal to, and this is an axiom which you will not question. Now, there is a counter punch to this which I will come to later on, which is known as, some people call it in terms of Boole's inequality, some people call it, we call it to be union bound, and myself or Uddala could do, I think we have few exercises on union bound. The union bound actually says that if these AIs are not necessarily disjoint, then the equality is replaced with a less than equal to sign. Now, whatever this, so I will come to that later on. So, but as people raise questions, so this is an axiom. What I am saying is you have events in your sample space that are disjoint, then you can just add their probabilities. Fine. Any questions till now? Okay. So, let us go forward. Now, using this you can do quite a lot of things. First, how do you prove? Yeah. The summation can grow more than, no, but I have kept the second thing, right. Probability of the sample space is equals to 1, and so your union of disjoint events where each event is a subset of sigma, this union cannot grow beyond the sample space, right. So, this sum cannot get over the 1, and I have not talked in terms of the indices, because whatever these indices are, the same indices come here. If here it is I equals to 1 to n, then there also it is I equals to 1 to n. Okay, what about this exercise? How do you prove this? You can even do it simply, right. You have one axiom which tells you that probability of sigma is 1, right, and the complement is also in the, so it follows, right. So, try this exercises. So, similarly you can think of this. So, you can easily prove this from axioms, right, because A and A complement are disjoint sets. So, they would sum to 1, hence the result follows. This is a result I think which you might not have seen earlier. Okay, and if it's strict then this holds, if it is then this holds, right. Why? See, the point is when I am taking an axiomatic approach, you can't use any argument apart from the axioms and probably some arguments on sets that you know. So, if think of this, A is a strict subset of B, right. So, that means now you can write B as A plus B minus A. These two are disjoint sets. So, probability of B equals to the sum of two probabilities, out of which one is probability of A and the other is of some probability. Your first axiom tells you that any probability has to be positive, greater than 0. So, there is probability of B equals to probability of A plus a positive quantity or greater than equal to 0 quantity. So, then probability of B has to be more than probability of A, fine. Okay. So, do this as exercises. Okay. So, I would not write this. So, whenever I just forget about, so when I write this it actually means intersection, right. For to have a clarity on the notation, if I write two sets side by side it means intersection, yeah. So, come on, prove this using axioms only. So, again think of writing A as, yeah. So, use A complement B. So, A union B is full of A, right, and then B get rid of the part that B is overlapping with A, that is B intersection A complement. These two are disjoint, fine. And now you can write A complement B in terms of B as well. So, that is how A intersection B gets into the expression. Quickly do it. So, if you need help on this, then we will again do it in the tutorials. Okay. So, all of you probably know this, right. It is only that possibly setting things up in an axiomatic framework and deducing results, this thing you possibly might not have encountered, fine. Now, what about extending this? So, so this is known as principle of inclusion and exclusion, and now you want to write union of AI in terms of many intersections, and so this is summation of PAIs, right. Now, if you add this, if you write this, obviously you understand which side is greater, the right side is greater, right, because we talked of this Bull's inequality or union bound. So, you will have a subtracting term, that is probability of say AI1, AI2, right. There would be how many terms in there? How many such terms? N choose 2 terms, right, because you would look at all pairs of sets A1, A2, A2, A3, A3, A1, so on and so forth. Now, when you look into this, the right side is now smaller. Then you add another term, and this goes on. Or else you can write it as just A1, A2 up to AN, right. Now, if you are going to compute this brute force, how many terms are in there in this expression? Asymptotically tell me, how many terms are there in this expression? Huh? Right. So, you are looking at, look at the first sum. How many terms are there? N choose 1 terms. In the second sum, NC2. In the third sum, you go up, right? And this is like, this sums to what? 2 to the n, right? Because you are looking at all possible subsets of n. So, computing this brute force is not a very easy proposition. Whenever you encounter such expressions, be a little cautious. If you are handling the general case, be a little cautious. Okay. Exercise is prove this. How can you prove this? Again, start from axioms. Your base case would follow from axioms and then use induction on n, where n is the number of sets you are handling. Let us now quickly do, as Venkatesh said in the morning, it is like it's good to have examples and tutorials. Derangement. So, all of you know what is a derangement? So, arrangement is rather I would say derangement is completely opposite to what arrangement is. It's total mess, right? And what is the total mess? You have say n envelopes, as she said, and n letters, each letter designated for its particular envelope, right? So, letters to Calcutta, to Coimbatore, to Chennai, to Mumbai, so on and so forth, envelopes marked with the addresses for each letter. Now, we want to figure out, well, there is obviously you understand there is a inherent counting problem to it, that I want to count the number of cases in which no letter goes into its correct envelope. That is a total mess. So, this is derangement. Okay. Now, you can state derangement in terms of permutation. Think of permuting the numbers from 1 to n. So, you have n positions and you have this n numbers and you want to permute them such that they go into those slots. So, a fixed point, I will say a fixed point of a permutation is the case where the ith element goes to the ith spot, and the derangement is one where the ith element does not go to its ith slot for all I running from 1 to n. So, there is no fixed point of the permutation. When that happens, it is a derangement. Fine. So, this problem is clear. Okay. Now, the question is, I randomly now put the letters into the envelopes. I pick a letter from this envelope. So, I pick the first letter, I randomly pick one, put the letter in there. That envelope is crossed, I take the second letter, because it is a permutation. So, two letters cannot go to the same envelope. So, I take the second letter, again pick an envelope of an envelope at random from the remaining envelopes, put it there. This continues. Now, I ask you, what is the probability that this random assignment was a derangement, or probability that any random assignment gives you a derangement? Yeah, we have to figure that out. So, this is what I want, probability that a randomly chosen permutation is a derangement. This is what I want. Now, what do you think? This probability should be how much? Give me a guess. Give me a guess. Should depend on n, right? What? Give me a guess. Give me a hunch. The answer would be something like this. No, that is the deduction. Give me a hunch of what should be the answer like. I look at this and then I will subtract 1, rather I will subtract this from 1, right. Now, look at this event. AI is the event that the ith letter goes into the ith position, and then 1 by n is the correct answer. So, you feel 1 minus 1 by n is the correct answer. Okay, this is a hunch. We will see 1 minus 1 by n. At least I have one answer. Other answers? Yeah, no more answers. Okay. Now, first look at this. So, AI is the event that the ith letter is in the ith envelope. Now, if I take union of AIs, what does it mean? That I am covering all permutations for which there is at least one letter going into its correct envelope. So, this union AI covers everything which is not a complete mess. Agreed? Now you know principle of inclusion and exclusion, apply it. This is the sum of P of AIs minus sum of P of AI edges, so on and so forth. Okay. What is each one of the first terms? P of AI. What is the probability that the ith letter goes to the correct envelope? There are n choices, out of which one is correct, 1 by n, and there are how many terms in this sum? N. So, this is n into 1 by n. What about the next term? Two goes into its correct position, right. So, the first one goes, that probability is 1 by n. So, NC2 will come later because that is the number of terms. So, 1 by n into 1 by n minus 1, right. So, that is n choose 2 1 by n into 1 by n minus 1 plus dot 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 dot. So, finish it now. So, the next term would be n choose 3 into 1 by n into 1 by n minus 1 into 1 by n minus 2, so on so forth till the last term. So, here you have 1 by factorial n and the index would be minus 1 to the power of. So, if you do this correctly and if you cancel out things properly, this looks like this, right. So, if you do this, if you work out this algebra, this would come to this. So, this was the probability of all kind of this non-messy things. So, what should be the final probability? So, this should be, I mean, I should not say it is exactly, but it is approximately. Mind you, we solved this problem without doing any counting almost, right. So, go back, when you go back to your homes, do this problem again, It takes a little while for this result to sink in. This is telling you that asymptotically, the number of letters really do not matter. As n grows large, this probability is approaching e to the power of minus 1, 1 by e. This is independent of n, asymptotically. Fine. So, that was an example of inclusion and exclusion. Quickly do union bound. This is a result which we will keep using again and again, again and again. Now, see, when you, for example, when I did this example on derangements, it was easy because I could handle this AIs, AIJs, AIJ, AIKs, all these k-way terms. But when you look into real life examples and you do a probabilistic modeling of it, there would be times when getting these intersections and having an estimate on their probabilities would not be that easy. At that moment, union bound is one that allows you to put a bound on this probability, that no matter how these events intersect, no matter how they are related, this holds. So, the union bound is like what I said at the beginning when I was discussing the axioms. It is right. So, we will see nice examples of this in the tutorial as well as in a few of the lectures. So, what is this saying? That see, I did not have any restrictions on these events. So, you take unions, and again it is like for our case, as I said, this holds for countable sets. Fine. Uh, think of writing a proof for this. Okay. So, take an exercise. Prove it. We will do it in the tutorial as well. Again, you have to start from axioms and build on. So, you have to write union of AIs again in terms of some disjoint sets. The challenge of this proof is, how do you write union of AI in terms of some disjoint sets? Okay. I'd rush a little bit. I would not go into this proof, neither would I go into an exercise on union bounds. Maybe we will do it in the tutorial. Okay. Now, let us quickly jump over to conditional probabilities. So, what is a conditional probability?
Of event A B is only a probability of an event given that particular event is occurring.
And this you know to be by? Okay. Now, what this is telling you is, earlier you had the sample space omega with you. Whatever probability that you were doing, so defining those measures, defining these looking at those axioms was on the sample space omega, right? Now, this is asking you to focus your attention only on the set P. Now, see, the moment this entire theory that I had built till now was on the sample space omega. Now, you have come down to B. What is the guarantee that this quantity that I have written, this probability A given B, is also a probability measure? This might not be a probability measure. I have to first verify that this quantity on the left satisfies all those three axioms. If it does, then I can continue doing whatever I was doing earlier with sets on probabilities. See, this A given B is really not a set, right? You cannot say it in terms of a set. Earlier you were defining probabilities on sets. Now this is telling you A given B, and then you have this nice definition, fine. Who said this is a probability? And if this does not satisfy those axioms, then you cannot do anything further with this, right. So, take this as an exercise. See, what actually happens here is, you replace A with B. On the right, what you get? 1, right? It is B intersection B, that is B. So, probability of B by B. And there is a small caveat in here, that I require probability of B to be strictly greater than 0. So, B has some probability mass in it. So, this is telling you probability B given B is equals to 1. In your earlier axiom, what was it that was having the probability equals to 1? Sample space, right, the entire sample space. So, this is telling you that your new sample space is B. I will not look here and there, I will just focus on B. So, that is conditional probability. Now, a nice follow up of this is, Now, there is a nice extension of this which we will do and you can prove. It tells you that this is known as the chain rule. So, I am looking at the intersection of n events. I can write it as multiplication of so an intersection, an n-way intersection, I can handle it using conditional probabilities. How? I take the first term, multiply it with A2 conditioned on the first term into A3 conditioned on the intersection of the two events, so on and so forth, right. You can see an easy proof of this. What you do is essentially, again this holds when all of these probabilities have non-zero mass, right, because always remember in conditional probability the conditioning event should have a probability greater than 0. So, look at each one of these terms. So, the second term would be probability of A1 intersection A2 by probability of A1. So, A1 should cancel out. So, if you write this out, what will happen is this cross terms would kind of cancel out and what would remain is the last term, which is the intersection of everything. So, this is a thing that I will use when we talk of min cut in graphs in tomorrow's last lecture, right. So, we will see a nice application of this later on. So, I say two events A and B are independent if this happens, that no matter how you condition A by B, B is not going to influence the probability of A, right. Now, if you open up the left side, it is probability of A intersection B by probability B. So, consequence of this is, now note that there is a symmetricity of this expression. So, probability of B given A should be probability of B, right. From there also you can come to this relation, that probability of A intersection B is equals to probability of A into probability of B. So, these are symmetric, right. If A is independent of B, B is independent of A. Okay. Now, quick exercise. What do you think? Yes, no, maybe, maybe not. Right. So, think over this exercise. The answer is they can never be independent, right, but think of a proof of this. Okay. Now, we handled independence of two events. Obviously, we want to extend this, right, getting to independence of a collection of events. Okay, maybe there the answer is no. Fine. Follow this notation a bit carefully. So, this is a very strong requirement. I am saying this should hold for all possible subsets of the sets 1 to ai to a1 to an. Then I say they are independence. So, this is a very strong notion of independence, right. Now, I would give you a small example where I will show, take a few n to be small and show to you that pairwise independence means that a1 a2 being independent, a2 a3 independent, a1 a3 independent, so on and so forth, does not necessarily imply that the events a1 a2 a3 are all independent, right. So, again Uddalak put this in an exercise, show that pairwise independence does not say necessarily imply independence as defined earlier. So, try to think an example where pairwise independence, there may be situations where pairwise independence imply mutual independence, but this will not generally hold true. You can surely come up with examples where pairwise independence will not imply mutual independence, and this result, this degree or level of independence will be very important when we discuss hashing and the space used when you use hashing. Maybe you can do another exercise after I discussed conditional probability. Look at derangement through the lens of conditional probability. Try to prove the same result that we proved in derangement through conditional probability. Okay. You have enough exercises to work in home, and myself and Uddalak would put this in a tutorial sheet and possibly give to Professor Somasundaram, so that by tonight things are uploaded, right. Fine. Maybe I will quickly move into random variables and finish the day, and then again take up tomorrow. Well, any questions till now before I get into random variables? So, what we have done is we have seen probability axioms, we have seen union bound, we have seen conditional probability, we have known what is independence, we have known that pairwise independence does not necessarily imply mutual independence. So, you have to be very cautious in there. when you talk in terms of the degree of independence. We'll quickly now get into random variables, but before that, any questions?
Mutual exclusive independence.
Uh-huh.
Mutual exclusive independence are two different things, or they are same term for the different.
No, that's what I said. Mutual independence means
Mutual exclusive and independent. These two terms have the same meaning, or they are
mutual.
exclusive
So, if two events are mutually exclusive,
and independent. Then what?
and then that means they are disjoint, right?
Okay.
Right? Exclusive means there is no intersection. So, they are disjoint.
And independent.
And then we have argued that
Yes.
I have given you an exercise which tells you that mutually disjoint events cannot be independent events. And this definition is the definition of mutual independence. Now, see, this is a very strong definition because I am asking you so that this holds for all possible subsets of 1 to n. If this holds, then I say that these events are mutually independent. Otherwise, they can be pairwise independent, they can be 3-wise independent, they can be 4-wise independence. But if you want the full scale of independence, then this is the definition. And it's a, mind you, this is a very, very, very strong definition. Okay, now quickly getting into random variables. So, a random variable x on a sample space omega is a function, or I might even say it is a real valued function that is okay. So, when you think random variables, you think functions. It is a function from a sample space to a set of reals. Say for example, you are forming random variables from your favorite dice throwing experiment, right. Your sample space consists of 1 throw, 1 to 6, right, and for each one of them you assign a real value, and that can be a probability, fine. Now, what do I mean by this statement?
At time particular t, the function.
Where do you find time?
No, no, all
There is no time in here.
okay. I want to say that at the real value for x is equal to a, what will be?
See, the point is, hold on. Mind you, probability is over sets. So, this x equals to a should give to you the meaning of a set. Now, think of this in your favorite dice throwing experiment. If I say that the sum of 2 dice throws where your sample space has 36 points is say 9. So, I write x equals to 9. What does that mean? That 3 6 is one that gets to 9, 4 5 is another that gets to 9, 5 4 is another that gets to 9, 6 3 is another that gets to 9, right. So, it is a collection of things in the sample space that takes the value a, right. So, this notation is now making sense to you. So, you can think it in terms of probability of some s such that this s belongs to the sample space and your xs is equals to a. Of now, before getting into independence or other things, let me define the expectation of a random variable. This is kind of the average value that this random variable takes. So, you have corresponding to this random variable, it takes a few values. Okay. Now, mind you, again as we are dealing with the discrete world, my random variable, the random variables that we would consider are also discrete random variables. So, that means the values that they take come from a discrete world, right. Okay. So, you will have their corresponding probabilities, and expectation is nothing but these things taken product together and then you sum them, right. So, simply put, expectation is nothing but summation x into px of favorite. Our favorite random variable will be a 1-0 random variable. This is one thing we will keep using again and again, and say it comes with a probability p, and so then this comes with a probability of, these are known as, in computer science we call them to be Poisson trials, where a trial has only two outcomes, like in your coin toss case, head and tail. One we label with 1, the other we label with 0. 1 comes with the probability of p and 0 comes with the probability of 1 minus p. So, then what is expectation of x? Which is, so p into 1 plus 0 into 1 minus p. So, expectation is p. So, what is p? P is nothing but, so the expectation of a 0-1 random variable is nothing but the probability of x taking the value 1. So, there is another result on expectations which helps us hugely, is known as linearity of expectations. So, for two random variables x and y, you can obviously make a generalization of this. So, maybe not today, but tomorrow I will define the notion of independence of random variables, but linearity of expectation does not care anything about these random variables. So, if you can sum up these random variables and take their expectations, it is equivalent to taking the sum of their individual expectations. This result even holds if n is countably infinite under certain conditions, but let us not get into that. For us, n is a finite quantity, right. So, linearity of expectations holds for countably finite many random variables. Now, think of this exercise. Say you have n cards with their faces down, right. What you do is you are trying to guess these cards. One guess is without any memory, say you do not have any memory. So, what you do is you go to a card and predict that it is, and this cards has these numbers 1 to n written on them, arranged in any arbitrary fashion. So, you go to a card and predict that it is this number, right. Mind you, you have no memory, you overturn and see. So, if you have said correct or not. Go to the second card, again predict and see if it is correct or not. So, this experiment is clear. The question is, on the expectation, how many correct guesses would you make? right. This is one problem. So, this is memory less guessing. We can do a memory guessing where you go to the first card, you open it, if it matches fine, you either way open it. So, it can be a match or a mismatch, but after overturning it, you know the number, now you remember it. Go to the second card. When you predict on the second card, you are obviously not going to say the first number because you have memory. Again you see it, you remember this two, go to the third, keep doing. The question is on the expectation, what is your number of correct guesses? Fine. So, do these two exercises to see as an application of linearity of expectation. Now here is another problem. You are, say you have gone to a shopping mall and they are selling, say, jeans of different brands, and you have a huge box consisting of jeans of all these n brands that is available, and the shopping mall tells you that if you buy jeans of all brands, you are going to get something for free. Now, the random experiment that you do is you pick a jeans, right, uniformly at random from this box. It is of a brand, say Levi's, fine. So, you have got one brand and this was a sure shot thing, right, you have picked a new brand. Now, you pick another, this can be Levi's or something else. Now, you keep picking up jeans till you get the second new brand. You have got two brands, but you have bought maybe more than one. Now, again you pick up something new. Do this till you get the third new brand. You keep doing this till you get n new brands. So, how many pieces of jeans would you buy on the expectation? Any hunch? Make guesses. It has to be more than n surely, right, that is for sure. And you understand that towards the end you have to buy more and more. Think about this. Okay, we stop here and again continue from the tomorrow's morning.